We are going, shall we wait a couple of minutes, Lee? Or we can start? Okay. Well, thank you very much for coming today. We have an impressive guest. No, yeah, guest.
Yes,
Yeah,
yeah.
I'm the host. Yes, you are the guest. Sorry for the confusion. Yeah. So, it's really a pleasure to have Juan Manuel García Ruiz with us today. He is right now a professor Iker Basque at the Donostia International Physics Center. But before he was a professor de investigación, the CSIC. Now he is also emeritus, right?
Mhm.
But he has recently moved to San Sebastian, and he's very happy there for about what I've heard. And today he's going to tell us this about the amazing research that he's been doing in the past and the amazing research he's going to be doing in the future regarding an ERC synergy grant that he has recently obtained. And in the past, he also had an ERC advanced grant, so he has been collecting ERCs. And so this can serve as inspiration for you young people. So you should take the initiative and also try to get these great grants. So he's an expert in crystallography and mineral auto-organization. And he also enjoys very much doing outreach. And today he's going to be talking about abiotic biomorphs, life detection, and the origin of life. So he's a great speaker. So I hope you enjoy the talk. And thank you very much, Juanma, for coming here today.
Thank you very much, Tasco, for the presentation and for the invitation to come here. This is a great pleasure to be here in the Centro de Astrobiología in Madrid. It's not my first time, but the first time was, this is the second time. The first one was many years ago, was starting, there was just starting this center. So we agreed to tell you about what we are doing basically now in my, as I should say, I was working in the Instituto Andaluz de Ciencias de la Tierra in CSIC in Granada. And then recently I moved this year, actually, to San Sebastian, to the Donostia International Physics Center, where I will develop there the new synergy project. So I will tell you about what we are doing relating with this project, right? So I was told that many of you are not probably geologists, and then to explain you what. So I think it's very important to talk about original life and primitive life detection. It's very important to know the geological framework, And for those of you that don't know well the history of our planet is 4.6 billion years old. So this rule have 46 centimeters. So I mean that every centimeter is 100 million years, okay? So if I just, just like some places here, some little movement here, I will remove humans, I will remove all the great apes, okay? So dinosaurs, that everybody believes dinosaurs is very old, some very old times, is here, okay? Here is the present, here is the original day. So it's here, dinosaurs are there. Cambrian explosion, in which we have for the first time clear multicellular fossils, should be here. And so we will talk about this part here, okay? This is the first 500 million years of the history of the planet, this part here. It's called the Hadean, because until recently, it was thought that the surface of the planet at that time was a dry wasteland, with a lot of lava, volcanoes everywhere, meteorite bombardment. So a place in which the probability for life, not only for life, but for prebiotic reaction to take place was zero, okay? It was the general thought until 10 years ago. Even today, there are still people that believe that the Hadean was actually a hell, because this is from where the name, the geological name came from, because everybody thought, particularly geologists thought that was a hell. So we have no rock from that time, no rock at all. All the rocks, Hadean rocks, disappeared. except very tiny crystal of zircon that give us a wonderful information about this time. There are crystal of zircon like the one you have here, this one. Well, we don't have, sorry. I think that we don't have, okay. Crystal of zircon, like those one, that tell us that 4.4, because this crystal appear in younger rocks, but they are actually from the Hadean time. So our colleagues, you know, that they date this crystal 4.2, 4.3 billion years old, okay? And this crystal tell us that at that time, just after the formation of the moon, even 4.4 billion years ago, we already have water condensed on the surface of the planet. This change, you know, I think it's something that I don't know why it was not a big news and a big, but actually it was absolutely extremely important information because changed completely our scenario for the origin of life, okay? So now we know that 4.4 years ago, billion years ago, there was already water condensing on the planet. And if water condensed at that time, everybody accept that this should do on an ultramafic crust. It's a crust, a solid crust, a thin solid crust covering the whole planet, in which you had mainly magnesium, iron silicate, okay? And this is very well known. This is experimentally proven, right? That when you have the interaction of water with this mineral, you trigger a reaction called serpentinization, in which they have basically the formation of iron hydroxide, the magnetite, and molecular hydrogen, okay? Molecular hydrogen. And the formation of serpentine is a kind of clays, and this is why the reaction is called serpentinization, okay? This is clear, and actually you have also information that at that time, in the Hadean time, the crust was a crust made basically by olivine and pyroxene. You know, the minerals that upon contact with water trigger the serpentinization reaction. So this molecular hydrogen, okay, react with CO2 in the environment and then form the methane, and because of Fischer-Tropsch and other kind of reaction, we have many organic compounds. So that serpentinization is very important in order to have organic chemistry laboratory, you know, at the planetary scale at that time. So you will see also there are other reactions in which you have like a Fischer-Tropsch that produce hydrocarbon and fatty acids and many other molecules forming at that time. So it's very important, this chain, because it means that at the very beginning, we already have organic compounds, and we already have a reducing atmosphere with methane-rich reducing atmosphere. In addition, this reaction gives a lot of hydroxide and means that the water, at that time, there was very high pH water. So we had soda water at that time. So the pH of the water, of the seas, of the pools, will be alkaline water, high pH water. And the other interesting thing is that as soon, because you have a high pH water, as soon as you have the first granitoid, I mean the silica-rich rocks at that time, then because the solubility of silica increased dramatically with pH, and pH higher than 8.3, you had the first deprotonation and the second deprotonation of silicic acid, and the pH of the water made the water rich in silica up to sometimes, you know, 10 milligram per liter. So extremely high concentration of silica that is exponentially increased with pH. So that the silica at that time, the seas and the water at that time was silica-rich, alkaline pools, lakes, and seas, okay? So for how long this reducing atmosphere take place? We don't know. This is something that is under discussion today. we don't have data, but what we believe in our groups, and it's increasing because 10 years ago, most of the people thought that the water were acidic and the atmosphere was not so much reducing. It was basically a neutral atmosphere, carbon monoxide and CO2 rich. Now there are more and more people, there is a mounting evidence that this scenario will be something like that. So at the beginning, you have a methane-rich, hydrogen and methane-rich atmosphere, in which you have still CO, carbon monoxide and CO2, and later on, this is moving towards CO2. So towards CO2 high atmosphere. So we will have a reducing atmosphere for a while. This is something that many people now accept. The problem is the wilds, okay? But this is why I have this, because wild means that maybe only 100 million years. And this is the point, 100 million years. And 100 million years or 200 million years is a huge amount of time. So it's something that is changing now, that we have the Hadean, we can consider the Hadean a time in which we can have prebiotic reaction. We have, let's say, habitability, you want to name that way, okay? But this is a place, we have now, it is playing in the problem of the origin of life, okay? So this is the new way to see the Hadean, evidence for water. So life that was considered to have started 10 years ago or 12 years ago, in the age of Archaea, more or less, okay? Now we know that life could appear, in the age of Hadean or the D of Hadean. Okay? This is important because that means that it's almost 1 billion years before, which we thought before. Okay? Now, why silica is relevant? Because our project is about the role of silica in early Earth and in the origin of life. Well, first of all, because silica is ubiquitous in the aircraft, particularly in the Archean. So one thing is important is to realize is that all these Archean rocks, all the rocks there, we don't have rock from the red part, okay? But all the rock here, all them are silicified, all them. So that means that the mobilization of silica during the Archean and supposedly also, during the Hadean was extremely high. Why? In our view, because the sea were alkaline sea, and therefore they facilitate very much the mobilization of silica. Okay. Second is that silica high pH has the ability to induce the interaction of carbonate and metal hydroxide with silica and forming self-assembly hierarchical structure, that behave in some way similar to life, particularly from the morphological and textural point of view, but also on the chemical point of view. And finally, and this is was most modern in our work, is that silica, probably through silanol groups, is able to catalyze key prebiotic reaction, okay? So what I mean by self-assembly? So what you see here, all these are non-biological. So these are purely, not only purely abiotic structure, but purely inorganic structure. There is no organic matter there. So in silica carbonate biomorph, these are interaction of silica in the growth of alkaline earth carbonate, like a barium carbonate, calcium carbonate, strontium carbonate, to form this fascinating structure. And this, when you have the interaction at higher pH of silica with metal oxyhydroxide, you have the formation of this membrane that are able, we already proved, able to catalyze selectively the formation of molecular brick of life. So silica carbonate biomorph is appearing in the green area there. So high pH between 9.5 and 11.5, and then silica metal of the oxyhydroxide membrane on the left, okay, is in the higher part, higher pH, okay? I will not devote too much time, but this is what I call silica carbonate biomorph. They are nanocrystalline aggregate made of tiny bricks of crystalline carbonate, nanocrystal, with an average size of about 300, 400 nanometer by 40, 50 nanometer, that co-oriented one each other to form this structure with negative Gaussian, positive or negative Gaussian curvature, which is particular, this is something, a property of life, morphology of life, not of the crystal world, okay? They are purely abiotic, so actually purely inorganic, but they behave, as you can see, similar, very similar to primitive organisms, okay? And we know how they form because at the beginning there was many years ago, but I have a lot of problems to publish this because people thought that it was impossible, that say, well, the referees, time after time, they say, you made a mistake, probably you have a contamination in the experiment, and this is why you found this kind of thing. It was very difficult for people to realize that the inorganic world is able to produce a structure which morphology, look like the biological morphology. So this is the co-orientation of the crystals in the nanocrystalline. Imagine a disk like the one on top. This is there is the electron diffraction of this co-orientation. The Maltese cross tells you that everything is radial. The co-orientation of the crystal is radial, you can see here. So in principle, this structure will grow like a disk, but then we found that actually when this structure are growing, in some point, they stop and then just propagate from the singular point to abroad, You have different points like this one. And this point, what happened is that you have the curling of the structure, okay? So you have the curling of the structure, and then it's growing that way, curl the structure, then stop to grow that way, and then just propagate like a surf in the beach, a wave, surf wave in the beach, you just propagate, okay? So this is the curling, okay? And then we found that depends on the number of curling and if the curling is up or down, okay? This is chiral, left or right, and depends also on the curvature, degree of curvature of the curling. We can explain all the morphology there. So, for instance, you have these two propagating curling, in the upper part, the lower part, so with two different velocities, and then you have the velocity of the radial growth of the lamella, okay? And then you have the curvature. So all these three parameters explain all the morphology you saw in the previous there. So here, for instance, you have it's growing two curling ponds, there on top, on the left, on the right, on the left. They are propagating all the up at the upside or downside. One left and the other one right, propagate, and then in a certain moment, they meet and stop. So they explain you this leaf-like or hair-like shape. You have exactly the same now on the left, top on the left, on the right, exactly the same, but then one of the curve of the curling would be up and the other one will be down. So both are either left or right, okay? And then you see there is on top is on focus, the lower down is out of focus. One is up and the other one is down. So they are propagating like in the previous one. But now when they meet, you have the formation of the helicoid. So I explain you the helicoid. Here is exactly the same, but imagine that now the curling is propagating very fast, much faster than the radial growth of the lamella. And then what you have is the formation of what we call bread. Okay, this is structure. Okay, and here is exactly the same, but imagine now that one of the curling is the radius curvature is much larger than the other one. And then you have the formation what we call the worms. Okay, so we can explain all this kind from the structure. So it's purely inorganic. It's that That's a way in which we are able to produce this kind of life-like morphology, okay? The chemistry behind, well, this is the explanation that we have. As I told you, this occur always at pH higher than 8.3, so that in which we have a strong variation of solubility, positive variation of solubility with pH. And then you find there that, imagine that you had the growth from, okay? Carbonate precipitate in the growth from, and then the pH decreased because of the carbonate precipitation. In that moment, there is a supersaturation with respect to silica, and therefore silica precipitate and inhibit the growth of the carbonate crystal. This is why we have very tiny nanocrystal. And then with silica precipitate, the pH increase, and then you will have a higher supersaturation with respect to carbonate, and then carbonate will precipitate again. So it's a self-feeding mechanism, okay, self-feeding mechanism in which the growth of the crystalline phase provoke the impurity that inhibit the growth, and the impurity provoke the precipitation of the carbonate phase, okay? So this is provoke an oscillation of pH in the growth from. It was very difficult to prove, so we have a model, to explain it. But then, we were trying to, and thank you to Marco Montalti and his team there in Bologna. So we were able to show that actually you have a oscillation of pH with time, okay? And explaining, the formation of this fascinating structure that we call biomorphs. The interesting thing with respect to life detection is that, when people found paleontologists, micropaleontologists, Archean micropaleontologists, they found a structure in rocks, or this structure like one in LEH A401, the meteorite, Basically, the reason to identify morphologically this structure as biological phenomenon is because it cannot be explained by non-biological processes. So then we found at that time, we're talking about in 2000, that if you look, these are microstructure found in Archean rocks, in which, they look like very biological. All they are Archean rocks. And as you found something like a Western Bargoon, and you say, okay, this should be so complex morphologically, that should be biological in origin. The point is that when we compare that time with our structure, so actually we can mimic almost everything in terms of morphology. So that then we claim, and there is another thing, important thing, is that all the Precambrian microfossil or proposed Precambrian microfossil, all them has been found in chairs. Chair is silica, okay? So that not only the morphology, the environment in which the rocky environment in which they are found are the same that we are performing our experiment. In addition, if you want to explain the precipitation of chair at that time, there was not biogenic chair, obviously, and then there are two ways to provoke the precipitation of silica. One is temperature, but the other one, much more efficient, is little chain of pH, okay? So most probably these chairs in which the structure were found, that were produced at high pH. And in addition, the oldest one so far proposed are barytic chairs. So they found this microstructure in chairs in which you have a high concentration of barium, okay? So later we performed an experiment because our let's say microfossil, the biomorph, were not made of carbon, okay? But then we performed an experiment in which we just heat some simple aromatic, phenol formaldehyde compounds that, that was, everybody accepted that was very plausible in the early Earth. So we produce the biomorph in the presence of this organic compound. They absorb as expected to the silica phase, and then we heat to 350 degrees to make the fossil in the labs, and then the Raman signature was exactly the same in both of them. So then we published that the morphology, chemical composition, can be used as an ambiguous tool for light detection. So the problem is that morphology does not contain inequivocal genetic information. This is the claim. We never claimed that these putative microfossils were actually microfossils or not, because this is something that other people should decide. But certainly, I think that most micropaleontology, I think almost all the micropaleontologists now acknowledge that we introduced this falsibility, because I think it's improbable. The point is that, and this should be maintained, is that morphologies do not contain inequivocal genetic information. So only when biology defeats physics, when Darwinian evolution make morphology very complex, then is the only way we can use. And some people, not now, but in the past, people told me, Juan, you say morphology does not contain biological information. Well, do you think that this is not a fossil? Well, the point is, yeah, this is a fossil, but not because of the morphology. This is a fossil because of something that Baron de Cuvier called comparative anatomy. It's because you can really connect, the function between the different parts, the different compartmentalization that they have in this fossil to explain the functionality. So it's comparative, it's not the morphology. Actually, I don't know, you know this book, it's wonderful, Stephen Jay Gould is a wonderful, unfortunately already died. He wrote many papers explaining evolution, but one of them is the lying stone from Marrakech. Go to Marrakech, because many people go to Marrakech to buy fossils, ammonite and belenite and all these things. But Moroccan people, they are wonderful experts to make this. So that most of the fossils that you can buy in Marrakech are actually made by Moroccan people. And he was working very nice paper. Absolutely wonderful to explain how to distinguish man-made fossil, because morphology is not. It's actually comparative anatomy who tell you if something is a remnant of life or not, okay? What is the point with primitive light detection is that we are talking about so tiny things that there is no compartmentalization, so we cannot apply comparative anatomy. This is the main problem. So it's very important to delimitate where is the frontier between non-life and life. I guess, my proposal is that morphologically we cannot do it. Okay, so this is one other thing that we are doing with the material science. This is my student García. He did wonderful thing that so far we induce, right, by temperature, but by temperature we can control the morphology of the things. So we can actually make whatever we want. Every color there is a different temperature, so we were able to really control the morphology. This is something that we are now exploring, the influence of nucleic acid on the formation, the morphology of silica biomorph, all these things, okay? And also in nucleobases of, in silica metal oxide biomorph, there's a lot of work there, but I will not tell too much, because I would like to tell you about something new, the protocols. You are familiar, everybody, with the Miller experiment, right? So Miller, it was a performed an experiment when he was a young PhD student. It's considered one of the most elegant experiments in the history of science. He just put reducing atmosphere, a mixture of gases of methane, ammonia, hydrogen, and water, because the reducing atmosphere proposed by his mentor, Harold Urey. Okay, so, and they said, why not to make an experiment? So we put a mixture of gases there. So we mimic the atmosphere of the early Earth, and then we also mimic the water, the ocean there. Okay, and then we have some temperature, so to provoke some vapor, and then the rain. So it was a fascinating experiment. And then he demonstrated that by just pushing some energy there in the form of electric spark, okay, he was able to synthesize amino acids. And well, at that time, he only discovered amino acid, but now we know there are many other molecular bricks of life are produced with this experiment. This is fascinating experiment. The point, the experiment, you know, is experiment is performing in the borosilicate reactor. And everybody later, there are many people, you know, many laboratories who already made other experiments, also always use borosilicate reactor. And as I told you already, the borosilicate reactor, I mean, this is the silica, you know, is dissolved at high pH. And because, oh, sorry. So because of the ammonia, the pH in the Miller experiment, in the typical Miller experiment, is a pH about 11.4. That decreased during the experiment until pH 9.6 or right now, okay? So we say, okay, maybe silica has something to do with this because, you know, the reactor, everything was made on borosilicate. So we perform an experiment at the actual pH and then also a buffer experiment about 9, okay? So that we made 3 different experiments, identical experiments, but one in a borosilicate reactor, a second one in a Teflon reactor, exactly the same conditions, and a third one in a Teflon reactor with some pieces of borosilicate in the water, okay? And we did experiment at normal, I mean, a natural pH, and the other one in the buffer pH, okay? And when we perform the experiment, we clearly see that you have a prebiotic soup as expected in the borosilicate reactor, but in the Teflon reactor, and the Teflon with pieces of borosilicate, you are basically, you are thin, right? But actually, particularly this organic, solid organic matter, it doesn't happen. So actually, what we found is that the production for amino acid, well, maybe this is better. Yeah. So here you can see that 25 compounds are only in the presence of borosilicate, only in the presence of borosilicate. And 56 compounds are derived by electric discharge in the presence of borosilicate. Okay. So the borosilicate is key for the catalysis of the reaction. So what happened? Well, is that Miller made a wonderful experiment. In my opinion, this is an absolutely wonderful experiment. The problem is that he forgot. I mean, he mimicked the atmosphere, the reducing atmosphere, he made the water, but he forgot about the minerals. Because at that time, we are talking about 1953 and later, nobody thought about minerals have something to do with the origin of life, okay? But what we discovered is that the minerals were there, actually, were there. Because if he performed the experiment in a Teflon reactor, it will never got the result that because they are famous, okay? So this is, in my opinion, this is something interesting because it's a completely new way to see the experiment. So it's a way in which we realize now that it's not an organic synthesis in the gas phase, but mineral surface are very important, okay? Okay, but see here, also. So this yellow polymeric organic compounds are film, you know, the film, which is all this, let's say, meat in the soup that we can there, okay, all the salt. This is only formed in the borosilicate reactor, only in the borosilicate. So this film up there, you know, this yellow film, only formed in the borosilicate reactor. Actually, these are experiments performed by Christian Genuine. So we see there when you perform the experiment, okay, the borosilicate is transparent, but after 1 they start to have this brown color, okay? And later on, the whole borosilicate, the walls of the reactor are coated by this film. And this film is also forming on the surface of the water, okay? Just floating there as a crina, como un velo, in the surface of the water. This is the film there, so a scanning electron microscope there of the film. This is the characterization of the film that we made. So you can see that basically is a polymer. So what we found so far is that a polymer of HCM, okay, cyanuric acid. So this is very important because it is well known that there is a group of scientists that propose that connected with the RNA wall, this poly-ACNA is a starting material to explain or to go, let's say, easily to the RNA wall. So it's interesting that this is the composition so far. We are working very much now on trying to understand better there. This is the structure of the film observed at high resolution with scanning electron microscope. So they are forming by little particles, spherical particles, quasi-spherical particles of a few nanometers in size. You have 127 nanometers in size that form in this film. Okay, we think that this probably is that drop forming in the atmosphere of the reactor. Okay, in which this form there, the polymerization, because of water drop, polymerization induced by silica of this ACM polymerization, right? And then they just fall down, forming or attach to the wall of the reactor. But then, interestingly, it's something that actually we were looking for that, because of my idea of biomorph and silica, we're looking for that. And then you can see, but you can see the formation of spherical particles that they made some FIBs, cutting with ion bombardment this sphere, and then you can see that some of them are hollow. So actually vesicles, okay? You can see the vesicle there. Here are deflated because when you perform the experiment in the vacuum, then there is just it's like a balloon, in which they lost the inner volume, okay? And then you can see this structure. But then we look more and more, and then we found this is fascinating. We found this kind of structure. These are forming in the Miller experiment. It's pure Miller experiment. We are not doing nothing so far, nothing, or no publishing yet. We are doing, but no publishing yet, nothing more. It's pure Miller experiment. So this is what found. So we found there the formation of this structure. You see, it's under micron, so several hundred nanometers. We have this like a streptococcus morphologies, okay? This polyp type morphology actually is, you see that because we observe this with a microscope, but it's actually upside down, okay? They are hanging from the cream, from the solid film floating in the microscope. And you can see they are hollow, or they are hollow, okay? So that we call them protocells, because in some way, it's a compartmentalization of the environment in which the molecular brick of life are forming there, okay? So we have a simultaneous concomitant formation of the molecular brick of life in Miller experiment, plus, the formation of these vesicles that could add a microreactor, okay? Not only because the poly-ACM forming the membranes of this protocell, that they could, self-organize, due to different kind of reaction. This is because also everything inside of this protocell could also react, searching for further complexity, and still stay there inside compartmentalization of few tenths of microliter. This is actually how they look like. Should be, this is floating. So that you can imagine little ponds, okay, little ponds in which you have the silica-rich water and forming this cream. This, I don't know how to call it, this is velo in sherry wine, we say the velo, el velo. So it's just floating there and then hanging all this structure there. So it could be millions of places in which you have there. So we call vesicular biomorph. You have the whole now happening. This is all these protocell of the biomorph are connected to the film. Okay, they are connected to the film. So it means that you have the film, and from the film, yes, they are hanging, but they are connected to the film always, and they are hollow. Remember. So this is the explanation that we have. This pure bubbling so far is that we have the formation of the ACM polymerized to form all these nano sphere forming the solid film. And then in a certain moment, when you start, this continues producing ACM, the ACM, go through the film, okay, and then they go deeper in the film, and then in a certain moment, the ACM and probably other gases that we are not able yet to identify is forming there, and then just produce in contact with water, they produce the bubble, and the bubble there is a precipitation in the air or the gas liquid interface. Okay, and then you have the formation of the sphere like on top there. But then if the sphere is forming, it's not just completely closed, then you can have another bubble form. And then you can have the formation of this septate, septation in the lower part. And you have the bubble is forming, and then still you are pushing, they become elongated like the polyp-like that we observe in B, okay? So that this is the explanation, is something that we know how to do. The point we realize it is feasible, or this is we can expect to have this in an open-air atmosphere in the early Earth. This is something that, well, we are working on that. But the point is that because it's silica there, we also showed that, Christian were performing all this experiment. It's an excellent experimentation, that also analysis with other colleagues. And we saw there are silica in this vesicle. So could be also possible, we are working the interaction of silica polymers. Could induce the formation of complex organic molecules that will, in a feedback, will also interact with silica. So we are working also in detail in the interaction between silica and organic compounds, and trying to see how far we can go in this, let's say, abiotic evolution. So just to conclude, our results suggest that 4.4 billion years ago, both the synthesis of prebiotic compound, the formation of poly-ACM protocell, already works. So it means that if this is something realistic, let's see what happens, But this is something realistic. We have everything ready from the very beginning. From the very beginning. So it's very easy. It's very easy to have the molecular brake of life. And now we know that in the same environment, it's very easy to have also these protocells. Okay, so this is something that move everything. It was actually here, right? Just after the formation of the moon, we will already have something that from the very beginning you have already the brick that you need to have the self-organization, and that means that we have because still we are discussing, but most probably I think that we can agree that some particular stromatolite 3.4 billion years ago, so something like here, already is approved for life. Okay, so it means that we have about 1 billion years, in my opinion, for lottery basically to make lottery. So to put reaction that we have what I call, I think it's here. Yeah, that is a long time. We have proto-worlds, not only here in this planet, but in many of the planet, hell-like planets. There should be billions of hell-like planets, and this thing could happen there also. So that from the very beginning we have it. So why we have no life, observed life, extraterrestrial life so far, Well, probably it's because during this time you have lottery. So there are evolving chemical system, looking for higher complexity. Some of them will reach something like life, or even something different, but also as complex and as life, the life we know. But other one will just do experiment, could be a good reaction, other reaction, more reaction, but probably will never reach something, let's say, interesting for us, right? But in my opinion, the point is that, yeah, it's a completely different point of view in the sense that we can think now that there are many planets in the universe with everything ready to make the life that we know, but that they have not the possibility. Probably why? Because like in evolution, like in Darwinian evolution, there is not direction. It's just try and error, try and error, try and error, and this is probably what happened at that time. And so this is what we call proto-worlds, okay? So the thing that could develop the life we know could not. Just, the trial and error, and to have different kind of material. So, and the other interesting thing for us is that, so I think that now the frontier between life and non-life is less clear than ever, either morphologically and chemically too. So I think now, for instance, we go to Mars, and I belong to ExoMars teams, but if we found this fascinating structure there, and we found amino acid and the 5 nucleobases, no, I think it will be we should not say that we found life. Maybe we found some proto-worlds, but not recently life. So this is what we are doing now. This is the project. There's a lot of silicon down life on our planet. So we have a colleague from Bremen, Professor Wolfgang Bach. He's an expert in serpentinization and rough fluid interaction. So it's very interesting for us because it is key for us to frame, the kind of geochemistry that we want to test. Marwan Suili, he's an excellent expert in geobiology, Archean geobiology and geochemistry. He's basically taking care of light detection. So he will perform experiment in which they will take actual organisms, microorganisms, but also our biomorph, the carbonate biomorph, the silica metal oxide biomorph, the biomorph that we are producing in the Miller experiment, and pure organic matter, high temperature, high pressure, and see what happens. So they can preserve. Professor Dennis Gebauer, actually, our co-PI was Helmut Kolfing. He's an excellent chemist, one of the people who led the two-step nucleation, and a completely new way to understand the nucleation process of crystalline material and non-crystalline material too. But he died 2 weeks after we got the project. So it was a shock. So we had to rework the project in some way, and then we invite Dennis Gebauer. He was his former PhD and postdoc student. I know very well. He's also excellent people who will study the silica behavior in solution and precipitation, and basically the interaction with organic to look for organic mineral extraction. Stephen Lalonde is a beneficiary with Mark Van Swillen, working basically in the same. Isaac Rodriguez Ruiz and Sébastien Teixenet, they are working in Université de Toulouse. And they will work because we are making some fluid dynamic microfluidics devices, to study some of this reaction in the Martian and early Earth atmosphere. And then Fermín Otalora was my co-worker for many years. So he's in laboratory with I was before in Granada. So he's also beneficiary. We will work together, in all these things. And this is what. Thank you very much for your attention.
Thank you very much, Juan, for this fascinating talk.
Thank you.
Thank you very
Thank
much.
you.
So we have now time for questions. Are there questions? Yes.
Well, first of all, congratulations for your synergy. We know that's not easy to get, and especially for emeritus professors or emeritus scientists. So
yeah. I'm now like a postdoc with 70 years.
lucky you are. No, my question is related to the pH.
To the
pH.
yeah, pH. Yeah.
I mean, it is true that alkaline pH produces interesting chemistry, but you cannot solubilize iron. And for life, iron is very important. What do you think about it?
Yeah. This is a problem for the approach, but we don't need to have so high concentration because you mean basically for the ions or because of the actual pH?
No. I mean, it's because at alkaline pH, iron is not soluble.
Iron.
Yeah.
Iron 2.
Iron 3.
No, but the iron 2. No, we are working with iron. No.
Yes?
Oh, yeah. No, this is, it's not. But we already show that if you have iron and silica at the pH in which you found the biomorph, a pH 9.5, 10, 10.5, you actually screen intense UV radiation. And we did this, yeah.
Oh, okay.
Yeah. No, iron is not, actually, Dennis Gebauer, he did an experiment in iron, and they, when we made the proposal for the synergy, we said we should introduce iron because it's important, it's key for many of these things. But then we said, well, but it will be very difficult to explain people because we want to focus on silica. Nevertheless, this was the third trial that we made, okay, because people saying that some panelists say that silica cannot be a catalyst. But then we published the paper on Miller, then it come. So we decided not to talk about iron, but Dennis Gebauer, he will work now, iron and yeah.
And just this Monday, it was a publication of the importance of meteorite striking the Earth to produce iron, to remove iron. I would like to know your opinion about that work.
Pardon?
PNAS paper that appeared this Monday that says that a meteorite...
My colleague sent me yesterday, but I had no time to read. Well, but this is, actually, this worked very well in our claim that you will have an alkaline pH there. Because in this meteorite, most of the rock will be actually iron magnesium silicate, and this is something that will work. The meteorite, in terms of, to me, this is we are discussing this in the group, and this is not really a big problem. Actually, it's something that will benefit because provide more organic compounds, provide a higher pH, provide a silica. So this is something that I think. But I have to read probably this evening.
Thank you.
Thank you, Professor, for your beautiful talk. I have a couple of questions. One, obviously, your research is at this moment is strongly experimental, but I'm curious to know if you are also, in addition to all the laboratory work, you are using some kind of natural laboratory. If you are visiting places with alkaline pH to check your laboratory findings.
You mean actual field trips?
Yeah. If you are using
yeah.
natural places where
Yeah.
to check your experimental findings.
Yeah, yes, this is very important question. Actually, this was my previous project. Yeah, there are very few places in the planet now in which you have alkaline water, very few. But there are still some of them. And actually, there is one wonderful one is for my project was Agua de Nez in California. And this is a well in which the pH is 12.1, and the concentration of silica is 4.5 grams per liter. So it was wonderful. So I went there. It is very remote place, very complicated to go. And then we took water, sampled some water from there. We made the experiment, and we showed that it's geochemical plausible. You can make biomorph and two types of biomorph with this water. So this is geochemically, it is plausible. So now there are very few places by the plausible. Then we went to, and actually we are working now in the Rift Valley. All the lake, they are called the soda lake. And the pH is about 11.4, so depend on the place, right? And the concentration of silica was high also, about almost 2 grams per liter. The problem is that about 10 years ago, the level of the water increased by 2 meters. So it was a disaster because all the facility for the tourists, everything was completely flooded. And for us, it was a complete disaster for the dilution of the water. So we have videos of people, Euster, and Robin Renault, that made, in the summertime, you go there to the lakes, and then you can walk and push there, and then you have like a flan, like a cream caramel. You have the silica gel forming there. I go every dry season, but so far we are not able to do. But we are working there too. And then also Oman. Oman is also a fascinating place in which we have very alkaline water. Yeah, there are some places in the water, and certainly also in water related with serpentinization in white smoker. White smoker also, yeah, we know that we can actually make this biomorph there.
Okay, my second question is more strategic or philosophical. I mean, we are not many geologists working in astrobiology centers. You are totally surrounded by molecular biologists, prebiotic chemists, astrophysicists. So you obviously are in the forefront of this business. So I'm curious to know your opinion about what do you think, which in addition of the role of silica in the origin of life, which hotspots of research do you think they are, or hotspots of research or main challenges within the mineralogical sciences? I mean, in the context of planetary science or and astrobiology, what could be, in your opinion, the next for the next future? Immediate future, the most exciting issues you identify?
Yeah, I think that there are many things to do.
Yeah.
Because, in my opinion, many of the space mission, exploratory mission, I would, in some way, looking for life detection when I always say, to Andy Knoll and John Gressinger, you are looking for life, probability is almost zero to find life. Why not to really make missions, to look for the geochemistry and geology? So I think that is now what we are doing in NASA are doing, and we plan to do in Mars is fascinating, I think. But to me, obviously the question, I think yesterday there was, I don't know here, the director of NASA, no, who was some woman here that actually said
the director of science.
But
NASA's director of science.
Exactly. Yeah. She say, and I think it's true. The question is, are we alone in the universe or not? Okay. This is, to me, this also the most important question. For that, I think that it is very important how mineralogy interact with organics and how mineralogy interact with fluid in the Martian or in Titan or whatever we want. So it is very important to have fluid rock interaction and organic matter to mineral interaction. For me, this is are two very important things. The other important thing, and is very, let's say, a very particular problem, but I wonder why in this experiment, silica is so important in the mineral experiment. Why? We don't know, because when people are like, oh, why? Well, I don't know. Probably silanol group. Often, if this is true, because for instance, we made another experiment, Christian is working on this, an experiment in which, as you can imagine, we know now that silica is important. So we made the experiment in Teflon, and then we put a quartz of crystal, just a surface of crystal, which is, we know is a right hand crystal. Okay, and then we performed the experiment of synthesis of amino acid nucleobase, and then we found that it is, I mean, the polarizer from the point of view of polarity symmetry is chiral. We are now working what actually is chiral, right? But the important thing is that in the quartz crystal, you can see very well that only on the surface of quartz the biofilm is forming. So I think it's very important to know this kind of interaction. We were talking before your experiment, your beautiful experiment of clays with polymerization to RNA, to form RNA. If you are right, and then why? I mean, what is there? What kind of bonds? What kind of a structure? Is the structure this important? The surface structure is a crystal structure. What is important? It's just because the point is that porosilica is not crystalline. So I think we need, because for me it's very important. I mean, mineral surfaces are very important for origin of life. So it is key to know what actually is happening, in the interaction between the mineral and the. Yeah, this is, and then, yeah, but this is not related to mineralogy, but also I wonder what other kind of protocol we can have in the universe. This could be important. Yeah.
Thank you very much for your fascinating talk. I have the following question, which is not going to be easy to answer, I think. When we do models, physics like doing models of everything, we need to know more or less which are in this case, the geochemical or even environmental constraints or properties of what we are trying to model. In the work that we are doing, we are working on, as you know, in the Hadean Earth that you explained before. And when I look up in the bibliography, in the literature, it seems that there are so many uncertainties that I don't really know which is more or less clearly true and which is not. So my question would be, how certain are you or are the scientific community that the sea was alkaline, that there was a lot of methane, all those things? In which situation are we? If you had to say which is the most probable Hadean Earth right now, which one would it be, and how certain can we be of that?
Okay, yes, very good question. We don't know. This is the yeah. No, what I mean is that so original life started to be a chemical problem. Miller until the 90s there was a chemical problem. Then biologists took the control and then become a biochemical problem. And at least now, we are thinking, oh, maybe Miller also have something to do. So that people now are interested in to know. And this is what we did actually. So from maybe 15 years ago, okay, we need to have a clear idea of the environment of the early Earth. And this doesn't matter if everybody agree or not. So then we have the group that we are forming, and there are many of the people, I think that more and more everything actually, now in the paper, sometimes there was a problem, say, the Hadean was acidic and there was CO2 rich. But we have, I think, many Klaus, you know that it was not true, and we know why, even historically, why people think that. So this view that I told you, I mean, I think that probably certainly not everybody will agree, but I think that more and more the first of all, serpentinization is key. This is something that now everybody realize, because it's the easier way to have molecular hydrogen. There's no, and to have organic compounds. There is basically no other way. Okay, so serpentinization is clear. To have serpentinization, then you need to water and then the crush. This is something that now we know that was the case. Now the point is, the people to know, okay, and if you have serpentinization, obviously you have methane, okay? Then the methane to and hydrogen ratio to CO2, this is a matter of discussion. But at the beginning, the formation, there was serpentinization and production of hydrogen and methane at planetary scale. So we should, probably there was a, you know, the volatile and disappearance of hydrogen could be important. But nevertheless, there was a while. This is what I think the people will not agree now. But I think that everybody now realizes that for a while, how much time is a while, we have a reducing atmosphere. And we are now, this is part of the project, is to do calculation about how much it would be, right? But this is the for original life study, right? Later on for the Archean, there is a lot of controversy. But this is very difficult. As I told you, we have no rock from that time. So it's really complicated. The good thing is that now we are going to Mars, to a place in which is the first window to that time, but in Mars, in Noachian of Mars. So this is why it's so interesting to the mineralogy, you know, at that time, and the geochemistry at that time. So I think the ExoMars will provide could have been even better, you know, but because the landing place is not, in my opinion, the optimum, but nevertheless will be very important. So we'll have much more information in the future. But if you want to have something for your model that everybody agreed, forgot about that.
Okay.
Thank you very much.
We have another question on Zoom.
Yeah.
So I'm going to read it and then we can close the session. So this is, and the question says, regarding hollow silica spheroids, I am not sure if I catch the exact mechanism of formation. And have you seen these structures incorporating any aluminum kind of protoclase?
Sorry, I promise you.
Let me see. So maybe Andrei, this is Andrei Ilin Moskalenko. Maybe, do you want to speak up? Can you? And then maybe ask.
Hello.
It's your.
Do you hear me?
Okay, so the question is, regarding hollow silica spheroids, I
Yeah,
am
like
not
the
sure if I
spherical
catch the
structure?
exact mechanism of formation, which was the bubbles, no?
Okay,
Going
yeah,
through the
It was
jelly.
mainly because
Yes.
of the bubbles and the crystallization.
And then the second
around those
question is,
bubbles.
and have you seen these structures incorporating any aluminum
Oh, yeah.
kind of protoclase?
Yeah, aluminum, maybe Christian know better than me. Did you find aluminum in the?
Wait, I'll give
No.
him the,
I don't think so.
wait for the microphone.
I mean, when we did like the elemental analysis, we can find aluminum, but it is also part of the sample holder. So it's not, we cannot clearly tell there is aluminum in these structures. But in any case, they are purely organic. So they are not silica or they are not inorganic materials. They are purely made of organic material. And sometimes we can find small amounts of silica in them, but aluminum, not enough to be sure.
No, puntero, pero que no. Ah.
Okay. That's
No,
basically
because, no, si yo le doy es que se pasa.
the mechanism.
Okay,
Thank you
anyway.
very much for the
So the formation is, so this is soft, is solid organic film. So it's It's a supernatant, this is just floating on the alkaline soup, okay? And then ACN is continually forming in the atmosphere because of the electric sparking there. So ACN, which is already saturated in the upper part of the container, so it's moving across the solid organic field, but we believe that there are other gases forming there, because otherwise it's difficult physically to explain the bubbling, okay? But we don't know. This is something we cannot yet. We are now designing reactor in order to have a better in situ analysis of the reaction, right? So, but anyway, the ACN is moving, and then as soon as the bubble, the gas enter in the solution, so they're forming a bubble, okay? And the bubble, the interface between the gas, because it's ACN, immediately will polymerize, well, immediately, depending on the concentration, polymerize, and then solidify the air-liquid interface, forming a membrane, instead of forming a protocell, okay? So this is the explanation for the spherical, for the A there. For the polyp-like B, is just the bubbling is forming, but the solidification is lower. The rate of solidification is lower, and then it takes time to to make a lagrima.
Yeah, the tear.
With gravity, yes, because it's forming there, it's forming, and then you have this elongated shape.
Like an eye drop.
Okay, and then the third one, this state biomorph, you have the formation of the bubble, okay, and then before it can really close, then you have another. It's a popping mechanism that is in physics is well known. So you have a popping mechanism, pop, 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 and then you have this biomorph. This is the mechanism that we don't have proof, obviously, because the size is very small. But we are now designing reactors in microreactors in order to really see with the microscope how they form, But I think that is, very plausible that we are right.
Thank you. And then one last very quick question.
Okay, a quick question, indeed. 2 quick questions. Sorry for that. I like very much the way you are revisiting Miller's experiment, and in particular these results. So my first question regards the role that the boron atom can play in the borosilicate framework. So if this is important, in this case, if we should expect a high boron concentration in the Hadean oceans. And the second is, as you have HCN and it's polymerizing and making these very nice structures, should we also expect the formation of adenine or other nucleobases? So somehow connecting Miller experiment with Juan Oro experiment?
Yeah, exactly. Yeah. To the first question, yes, boron, it is expected also to be very important. The problem is that now we are trying to find different kind of glasses with different concentration of boron and silica, so that we can really, respond experimentally to that question, which is really important. Okay. The second one is, I think that we are now, performing the experiment. So far, we only did the Miller experiment, nothing more. Now we are cooking. Now we have, so doing some, Christian already designed an experiment in which he can variate online, the composition of the atmosphere. That would be very important. So to move from methane rich to carbon monoxide to CO2 rich, so that see what happens. But I'm sure, adenine will form. Yeah. So this is. Pardon?
Perhaps at the end you have adenine.
Oh yeah, sure.
That would be great.
I think that we will. Also, we are now working to thinking is still not perform the experiment using sulfur and phosphor inside, because there is a very interesting thing, is that the problem of phosphor is a problem because phosphate precipitate as a calcium phosphate. Okay, But, and this is why pH, right? Because if you made plot on the concentration of phosphorus in phosphate in solution, okay, versus pH, it is straight line. So the higher the pH, the higher the concentration of phosphorus. Why? Because in a CO2-rich environment, or you have CO2 in the environment, as soon as you have high pH, all the CO2 in the water is in carbonate form. And then immediately you trap the carbonate, you sequester the calcium, and then it's impossible to have. And so phosphate is still remain. So it's very interesting alkaline water. So let's see what happens.
Very interesting. We will be inviting you in a couple of years' time to see the new results. Well, thank you very much for this talk and for the answers to the questions. And let's thank Juanma again. Thank you.
Thank you very much. Thank you.